Welcome to today's webinar, Rapid Design Iteration and Mesh Refinement for Rod Heater Simulation using Coreform Cubit and MOOSE. I am Matt Cederberg, Coreform's Chief Strategy Officer, and today's webinar will be presented by Paul Keutelian from Quartermaster Consulting. The agenda for today's webinar will be pretty packed full. We were talking beforehand, and Paul's sharing about 3 webinars worth of content today. First, Paul will share advice for how to get started with Coreform Cubit and MOOSE. Second, Paul will give a live demo about how to use Coreform Cubit for some of the core tools that he uses, such as geometry manipulation, web cutting, compositing, and meshing. Paul will then demonstrate how to automate complex problems with Coreform Cubit, MOOSE, and Python, and then we'll have time for a question and answer session at the end. To introduce Coreform Cubit is software used for advanced meshing for challenging simulations. And some of the key features of Coreform Cubit are the ability to import CAD data directly through various proprietary and open file formats, its strong hex meshing capabilities. A lot of people use Cubit because of its ability to do Python and scripting, and Paul will be showing some of that today. And one of the interesting things about Coreform Cubit when it comes to working with MOOSE is that both of those pieces of software are based on the Exodus file format, which has led to Coreform Cubit being one of the main meshers and preprocessors used to run simulations in the MOOSE finite element solver. So with that, let me just introduce Paul briefly. So Paul Keutelian is a systems and thermal fluids engineer who has used both Coreform Cubit and MOOSE commercially for several years. And we're thrilled that he has agreed to do this webinar with us. And with that, let me turn the time over to Paul.
All right. Thank you, Matt. And thank you, everybody online and watching. I'm really excited to be with you today and to share some of my experience with MOOSE and some tips and advice on folks getting started with both of these tools. I'm an engineer, so my perspective on these tools is a little bit different, perhaps than a fully scientific or developer perspective. I've been fortunate enough to work with a number of teams throughout the aerospace and nuclear industries over a decade to introduce modeling and simulation, other design practices, help educate new engineers coming into the industry on how to approach some of these problems. And I'm hopeful that some of this experience will be useful to everybody today. So I want to go over how I, as an engineer and as a consultant, think about meshing and refining assemblies with Coreform Cubit and MOOSE, and using Python to iterate on a design rapidly. These two things are very important from my perspective because the key for us is speed. And it's not just speed of how much time it takes me to perform this work, but also the speed of running the simulation itself. And finally, I want to show some of the benefits of using Coreform Cubit and MOOSE together in some creative ways to solve some of these complex problems. I want to start by saying that both Coreform Cubit and MOOSE have a number of really good reasons to use them. The top of which for me is the documentation and extensibility. Both of these tools have very extensive documentation online that let you reach completely into each software package's systems. And both of them are also intentionally designed to let you extend the software for yourself. And I'll have a demonstration of how I do that for some of my workflow. Second, the developer support and community is excellent for both. Both tools have forums online with active participation from the developers and also other community members that are trying to solve a problem. So these two things alone, the documentation and the community, the forums, are great places as engineers to start looking at solutions to problems that you're trying to solve, which other people probably have already tried to solve and have shared. And finally, the scripting and journaling capability. So Coreform Cubit has a strong Python scripting API in there that we're going to go through that is also another entry point for folks that may be familiar with Python, but not so familiar with using meshers and preprocessors, but that want to get into it. So it gives them an opportunity to understand the system a bit on their own terms and to be creative about some of the solutions that they need to come up with. The next is GUI customization. So when I'm running into new problems, there are, in any field of engineering, there are a lot of similar problems that show up. And so you can build a workflow for yourself pretty quickly within Cubit to help you do the exploratory part of your work rapidly as well. And automatic journaling. And I know many people have run into the situation where you get deep on a complex problem. It's very fascinating. You've tried different angles and finally you get it to work and you go, okay, how did I do that? And the automatic journaling allows you to reconstruct what you did quickly without having to remember to do it. And it also is very quickly convertible into automation. And what this means is that you as a user of Coreform Cubit and MOOSE have what I call first-class access to all the commands in the software. Anything the GUI can do, you can also do in Python. There's nothing obfuscated. There's nothing hidden. There's nothing only the developers can do. And transparent operations. One of the things that I appreciate very much about Coreform Cubit is that the output is very verbose. So you have an opportunity to debug anything and to be able to share that information with other people who may be able to help you and be told exactly what is wrong. And what's great is that there are links to all of this online in the documentation. So as an engineer stepping into any problem that I'm solving with these tools is to start by watching the YouTube channel. There are two very good playlists on the Coreform YouTube channel that has a wide variety of problems and a demonstration of a lot of the capabilities in Coreform Cubit. I use it very often as a reference for some of the extended or more advanced features. And then I go to the support pages, the documentation, which again, very extensive and has a lot of complete work. And then finally, the forums. And my strategy usually is to look for similar problems to what I'm trying to solve and to reconstruct that and slowly move from a solved problem to this new problem that I'm working on. And finally, I want to make a call out to the item wizard. In some of the documentation and some of the tutorials, the item wizard sometimes gets called out as a tool for some of the introductory beginner workflows in Cubit. As a person who's used this tool for a couple of years, I still use the item wizard because it allows me to keep a process together of all the different features and all the different steps that I have to go through to do proper meshing and pre-processing. Now, if you're just wanting to get started as fast as possible, my advice is to watch these two videos. Introduction to Coreform Cubit, hex meshing for beginners with the item wizard, and how to mesh a tire tread with Coreform Cubit. In the first video, Greg walks through a lot of the features and a lot of the how of Coreform Cubit's workflow and the tools and what it's looking for. And the tire tread tutorial gets a little bit deeper into what I consider some more of the unique or advanced features that let you really address complex geometries and difficult problems. So it's an hour and a half of your time, and this will get you, I think, most of the way there. So from all this, I have my process, which is based on what I've learned from using these tools, which is to import your parts, heal them, web cut them, composite them, imprint and merge them, and mesh them. And there are plenty of tutorials online about what each of these means and that go into the detail of this. How I use them is I use the GUI customization to create my own toolbar that lets me just walk down this list whenever I'm working with a new part or a new assembly to make sure that I'm consistent in my own work if I'm not using the item wizard. So I want to introduce a problem that I run into commonly if I'm joining a team as just a pure modeler. I haven't been a part of the design, and I'm just coming in to do simulation work and get a team off the ground and get them working. So I have here a vacuum chamber with some heaters inside, and the team has just given me the entire assembly because they haven't had time to cut out just the heaters, and I've been given some material specifications and some parameters that they want to sweep through. And they say the heaters are in here. You have, we don't know the part number, just go and look for it and get it done. So that's a pretty common workflow for me and the way I work. So Cubit makes it easy to deal with this, and I'll walk through it in a second. Before I do that, the top 3 things that I'd like people to keep in mind when in this situation is use the item wizard. The item wizard will help you keep a good discipline and a good process for your high quality meshes. There are a lot of features in Coreform Cubit, and there are a lot of good things that you should do. And the item wizard will help keep you on that straight and narrow path. And I want to make 2 call outs to features that I think are a little under considered, and that's compositing, which I'll demonstrate how it benefits meshing some complex surfaces, and then similarity selection. So there are a lot of pattern components, a lot of arrayed components, and a lot of assemblies, and they might be difficult to click and swing the model around. And similarity selection, again, gives you the speed to power through decomposing these assemblies. And finally, I want to emphasize again that the order of operations matter. So decomposing, then compositing, then imprinting and merging and meshing, keeping that high level thought process in mind is important, because if you do it in different orders, you may have to backtrack, or it might create meshes that you don't intend, and it can introduce some difficulty. So there's a lot of nuance to meshing that I think Coreform Cubit does a pretty good job of keeping in line for you. So with that, I'm going to jump into this brief demo to show this flow in action. So I have Cubit here. As Matt mentioned and other videos have demonstrated, Coreform Cubit has an excellent import capability that lets you pull any geometry from other CAD tools. And I want to call out too that, this is a pretty heavy assembly. It's got dozens of parts. There are some repeat parts in here, and opening this up in SolidWorks and NX can take a fair bit of time. And so even just getting to the relevant parts in Cubit is beneficial. Then again, if I'm trying to get to the heaters, it's easy to do, Control Shift Select and just clear out the materials that you don't need. We can start to see that the heaters are here underneath, and again, very lightweight. And here we can see there's some parts, there's some repeat parts here, and hitting the select similar volumes makes it easier to select these parts and then get rid of them also. And so we can see in 30 seconds, if I had no further knowledge about what the heaters are, what's in this thing, being able to use this tool will let me get there in under a minute. So for the sake of this demonstration, I want to go a little bit deeper and again, use similarity selection to select these bolts, these other clamps, and get rid of that, clear that away. And now I'm down to the heaters and these contacts. And I want to share a little bit, some tips about web cutting geometry like this. So this doesn't look that complicated, but what I've found is that web cutting, what you're trying to get out of this is you're trying to make it easy for Coreform Cubit's mesher to understand the cleanest way to produce a mesh. And what I have found is that there are 2 goals that I pursue. One is to try and get to hex meshing everything as much as possible. Hex meshes are nice because the matrix is a little bit stiffer, the solutions are a little bit more stable. They conform to geometry a little bit better, and it's fewer nodes. It's computationally easier because you have so many fewer nodes and connections for each of those versus like TET meshes. So with something like this, there are some corners here. There's some complex curvatures here. So I'm going to go ahead and work through this a little bit. So in this case, I'm going to say, well, I care about the corners. You could decompose this and just turn this into a smooth surface. But in my case, that's not the case. That's not what I need. So I'm going to start using these features to start cutting away and actually split this apart into multiple different bodies. In here, when I'm picking how to do this decomposition, I'm trying to, what I would like to do is use as much of the features of the geometry itself to define where the cuts are going to be, because that enables me later when I check the journaling file to have a consistent solution if the geometry changes. Like very much with these types of things, the team is testing out different parts and different types of solutions. So I can't very often rely on specific coordinates to work on. So as I do this, you can see in the history, this is keeping track of like specific vertices, specific locations, specific planes. And that's going to become handy later when I script this. So as you can see, I'm also cutting away at some of these wings here so that I can create rectangular pieces. And those have been a bit easier to mesh for me. And then here too, in this corner, this discontinuity, I'm going to want nodes at these specific positions too. So again, I'm going to make one more cut right here just so that the meshes between these volumes line up. And then again, from the tutorial, from other tutorials online, one of the lessons you learn is that you should mesh from the most constrained volume out. So I'm gonna isolate this one to be able to work on it. And one of the things I want to show here is now we've got to deal with this complex surface. So you can see these different surfaces here. It would be a many-to-many mesh, which would be pretty difficult to do. But by using the composite feature, which I've shortcutted here, I can now look at this volume, control click to select them all. And there we go. Now this virtual geometry has been created, which lets Coreform Cubit know that this should be treated as one surface. And then in the mesh definition, I can focus on the resolution of that surface. So now I've changed this many-to-many surface sweep problem to a one-to-one. So now we can go here into the mesh. If I'm, again, a lot of my teams are not worried in the early phases about specific solutions to things. They're worried about a general idea of where things are to concentrate on. So if I'm doing that, I can assign this a map surface mesh. And then for sizing, in this specific case, automatic sizing actually works out okay for me, because again, they just need a general case of it. And this comes with your own experience with the tool where this is. But of course, Coreform Cubit has many of the other features as well. So I'm going to do this surface up here, and then I'm going to make sure to apply the same properties down here and mesh these two. And then from your multiphysics, from your modeler, so in this case, MOOSE, there's documentation on how many layers of nodes should be between top and bottom layer to get good solutions. So I believe the solution in MOOSE is at least 5. So I'm going to mesh these as a curve. So I've got these two surfaces, I've got this target, and now I can mesh this volume. So I've given Cubit enough information to be able to sweep through this properly. And it's pretty good at the auto direction. I'm going to give it a little hint by saying sweep in -y. It's a pretty close axis. And there you go. In just a few minutes, I've created this mesh just for this object, this volume. There are plenty of tutorials about how you take these volumes and combine them together into single bodies, which is how you'll be able to work with them within MOOSE. Now I want to talk briefly about automating some of these complex problems. So like I mentioned earlier, we do a lot of part sweeping and variable sweeping. So depending on maybe the heater length is different or the clamps are thicker or something like that, you can apply different voltages. They'll be in different conditions, that sort of thing. I manage these in a table that has all these different parameters together. So this is what that looks like. And this master CSV file is split into the part numbers that I would be working with in Coreform Cubit and the import file. And then to MOOSE, I would be sending either single variables that would be modified that I want to sweep, or MOOSE itself has a parametric modeling system in there too, where I can put min maxes and have it actually sweep through those parameters. So this is what that step file would look like, or that CSV would look like. Then this all feeds into a master Python script, which is straightforward. You're importing your table, and then you are pushing the relevant part numbers that you want to assess into Cubit, and then the test number. And what you're getting out of that is a Cubit export or an Exodus export that I name after the test number. That way I can keep track of it. You can also add additional Python in here to add a new column to the input CSV to say this is your as run solution. And then finally, I'm pushing this to MOOSE using the command line parameters that let you modify specific variables in that specific run. And then looking into the Python script, so the Python API, as I use it, as I see it, is there's the read-only information gathering API, which lets you get information about the volumes and surfaces so that you can process it, make decisions on, and kind of organize how the flow is going to work in the script. And then the second mode is the command API, which is the Cubit command language decorated with Cubit.command that you can issue from Python. And this is good because it lets you visually also separate parts of the program that are doing one versus the other. And again, documentation there is great, and you can explore it in the GUI and get the commands you need out from there. And as I was working through this demonstration, there are patterns of part numbers, or part numbers are repeated. So I would be the one doing the exploratory work to find out what these part numbers are, and then document them in the input CSV, and then run them through the Python script. So I would mesh the first of a kind of these things, like I would mesh a heater, I would pull the journal file commands, build the scripting from them, and then put the part numbers into that input file, and then iterate through using the Python flow control. And so sometimes you get lucky, and Coreform Cubit is smart enough to be able to deal with similar enough geometry. So in the demonstration, there were curved heaters and straight heaters. And where I start from is saying, well, if I can do a simple solution like a straight heater, and how we mesh that from the journal file, what if I just applied it directly to the curved heaters? And sometimes it works. And Cubit's pretty good about that, which means that the code is identical. In fact, in this segment, only the part number is different, and I was able to keep the rest of the code the same. So now this starts to go into my library of functions that I can reference. And as I run into similar parts out in the world, I already have a meshing scheme to address this. Next is looking at the MOOSE input file and how this script interacts with MOOSE itself. So for engineers that are just getting into this, the MOOSE has this command line usage where you can inject changes in variables without modifying the input file itself. So that lends itself to Python scripting, and it uses kind of this directory structure definition to reach into the blocks in your MOOSE input file. So where you have kernels, then the a kernel subblock, and this coefficient variable, you're doing the same thing. You're reaching in from the command line to make this modification. And in that way, you can iterate through. Then if you're doing a parameter study, MOOSE does that too. And there is an input. You would add the parameter study block to your input file, and then do exactly the same call with your high-low values from the command line when your script runs. And then from there, you can, kick it out to your batch scheduler, or if you're running local, you can have it wait and run on its own. And so now I want to briefly talk about automatic meshing within both of these tools. So this is one of the curved heaters I was talking about. These are just the generic parameters for it. Sometimes you find yourself in a situation where if your mesh isn't correct or isn't good enough, you can start to introduce some pretty unphysical solutions like metal wrapping up over itself or expanding in weird ways. And some of that has to do with the accuracy of the mesh to the physical world. And the other part is the gradient of the solution in that mesh. And for the gradient of the solution in that mesh, MOOSE has this adaptive meshing tool. For the other one, the similarity of the part to the real world, Coreform Cubit has excellent analysis tools like analyzing the Jacobian and that sort of thing to make sure that your description is appropriately accurate. But looking at the MOOSE auto mesher, it's going to look at places where the solution has a high gradient, and it's going to add additional nodes to try to give you more physical solutions and stabilize the answer. And it's great, but it is very intense and it's very computationally expensive. You can see how the node count can increase quite dramatically here. But what is nice about it is that the auto mesher it creates its own checkpoints as it tries to iterate through making finer and finer meshes. And while the simulation is running, you can actually pull these out and you can load them into ParaView, or you can load them into Cubit to take a look where certain physical points of interest are going to be, like physics-based points of interest is going to be. So if I didn't understand electromagnetism, if I didn't understand how heat worked through one of these heaters, and I didn't quite know where to put the nodes, I can start the program with the auto mesher, let it create one or two of these meshes, and then see, okay, this corner is thermally interesting or electrically interesting. And then it may be faster for me to remove nodes in places that aren't interesting and put more nodes here instead of waiting for the auto mesher to do it. And once you do that, it's the same thing. You're importing the geometry, you're decomposing the features, you're doing the meshing on a single part, iterate on the journaled instructions, and then do it for all the remaining parts in your assembly. And that can make pretty dramatic differences in how quickly you solve a problem and how accurately you solve a problem. And in my line of work, accuracy and speed are very important, because a lot of these companies, the cost for a consultant or a person dedicated to modeling and the computational cost, are pretty equally competing line items in the budget. So that's how you can get some edge to that. With that, I hope I've been able to share some strategies around these learning objectives, and I'd like to thank Coreform and the MOOSE development team for all their work on these tools and being extremely responsive and helpful for us. And with that, I hand it back.
We do have a few questions, and if there's other questions, feel free to type them in and we can address them now. So here's a question from Travis asking, is the Cubit API limited to just using Cubit.cmd calls?
No. So there's in the documentation, there's a read-only API that is that uses Python objects and methods to get information about the volumes and the surfaces and the geometry. And the Cubit.command calls are for making changes to the mesh itself. And that's how I use it. That's my understanding. So
Great. Okay, yeah. And Greg Vernon, I noticed that you unmuted. Do you have anything else to add there?
Yeah, what I would say is that so that CMD again is just passing in the Cubit command language, and your Cubit as a geometry-based mesher or CAD-based mesher has a very strong tie to the underlying geometry kernel. And just the most robust way when you're in Python to talk to the underlying kernel, which is written in C++, is to use these Cubit commands that are highly tested. And so that CMD is really just that most robust way to do that. There are for kind of like edge case power users, there are methods in the API where you can create and modify geometry, but it starts creating pointers that start to pollute your Python space, and Python doesn't really know what to do with pointers and references. And so it's just that CMD is really just the workhorse for making modifications to your session for that reason. But yeah, there's in our documentation, we've recently cleaned up the documentation a little bit. I don't know if Matt or Paul could go to the documentation to show this, but we've tried to break it down. Yeah, if you go to the Python API into like this method-based API, which are kind of the probably the 95 to 99% of the methods that you will use when you use Cubit Python, as well as then the object-based API is another method for being able to get information about entities in the model. So you can query a volume, and then from that volume, there are methods, say on the volume, to compute its center, compute its volume, and so forth. And so, yeah, it's a really rich API. And then because it's so extensive, we've tried to put, again, just like the 90 to 99% of the tools that you'll use here. And then the appendix has the complete API, which is auto-generated from the C++ SDK. So there's a ton of functionality here. So certainly not just limited to one or two methods.
Great. Thank you, Greg. Paul, another question about MOOSE. So MOOSE, of course, is open source software developed out of Idaho National Lab. As a private professional, why are you comfortable using open source software, and why did you make that decision to use that in your practice?
Sure. A lot of the teams I work with, our design methods involve physical testing to anchor your models. That's what we call it. So what we do is, what you're trying to do in modeling and simulation is you're trying to build a tool to predict what your changes will result in. And that starts by being able to describe something that you have. And so in the workflows that I work with very often, there is an experiment that I can tie a model to correlate it. And so in this heater example, we can use an IR camera to actually verify that those points are the hot points and what temperatures they are. And if I'm able to use any software to describe that accurately and do that for a few points in some test bounds, there's a lot of comfort you can gain from that you can make predictions about what the outcome of your next design choice is going to be. And that's how you build the confidence with that. But I would do that with paid tools also. And I have.
Okay. But MOOSE in particular, is there a reason that you are choosing to use this open source software over paid commercial software?
Oh, I mean, in obvious, well, two reasons. One is the cost of it. But the second one is access to the developers and access to the inner workings of the software. If there are questions about how it works or specifically the math that's going on in it, I have found MOOSE to be much more transparent about how it's working and what's going on. It is more work. It takes more in-depth understanding of what it is, but it also builds a lot more confidence of like what is actually happening under the hood.
Great, thank you. So the question, if I do web cut in Cubit and mesh the part, then do I need to merge that with other parts to proceed for a simulation?
Yes. And yeah, so the merging, Greg can answer this much more clearly than I can, but imprinting and merging, my understanding of it is that this is what lets these volumes and these bodies line up the nodes with each other so that you're not having to do like nearest neighbor node connections or any interpolation between these contact surfaces.
Yeah. And that's a perfect explanation. What ends up happening is that, again, Cubit being a CAD-based mesher, it meshes the lowest dimensional entities first. So if you say, I want to mesh volume all, what happens first is it goes through and it meshes the vertices. That's obviously trivial. And then it meshes curves and it meshes surfaces. And then it meshes the volumes. It propagates, these surface meshes into volumes. And so when you do an imprint and merge, you can imagine that if you have two surfaces that don't have the same shape, so maybe like a cylinder on top of a box, the imprint communicates or projects and then kind of Boolean adds this circular surface onto the square, if the circle is smaller than the square surface of the box. So that now there are two surfaces that both have the exact same topology. There are these two circular surfaces. Merge then says, nope, there's not two surfaces, there's only one surface. So then when Cubit comes through and meshes all the surfaces, it meshes this one surface that's then shared by both volumes. And so then that, by construction, means that those two volumes are now connected through this shared surface and these, whatever elements you have that are on that one single surface. So that is a very good point, that if you want a contiguous mesh, then you will need to do that imprint and merge operation, which again, I think, Paul, you mentioned that we typically like to do that after we do compositing, because compositing can get rid of a whole bunch of extra, maybe like really small curves or redundant surfaces and stuff like that, so that then your imprint and merge is cleaner.
Yeah, exactly. And it's also after you've done any defeaturing. So you're not having to fight corners and angles and that sort of thing.
Yeah. Great. Well, Paul, thank you again for all the preparation of the webinar. This recording will be made available to those that attended today. And we'll also make the slide deck available so you're able to access the references that Paul linked to from there. And again, Paul, thank you so much, and I hope everyone has a great day.